Hello everyone, welcome back to you all in this new video where we are going to see the manual approach for the design of your long column. This complete problem we are going to solve in a few important steps. In the first step we are going to see the problem statement and the classification of the columns as per IS 456-2000. In the second step we are going to determine the additional movements due to long column effects. In the third step we are going to finalize the design movements about both the axes as X and Y. In the fourth step, we are going to check for the adequacy of provided section and reinforcements. And in the fifth step, we are going to do the design for the main and lateral reinforcement. And in last, we are going to prepare the schedule and detail as per the design results. For better understanding of everything, you have to watch this video till the end. And if you are interested in the field of structural design and you are new on this channel, so we are continuously uploading this kind of videos. So please subscribe this channel and share this video with all of your friends and press the bell icon to get every notification. First of all, try to understand the problem statement. So we have to design a RCC rectangular column of size 300 by 500 in mm and the floor to floor height is 5.6 meter. The material to be used as M25 and AP415 as concrete and steel respectively. The beam which is connected with your column is having the size of 230 by 400 in depth. We have to assume the effective cover for the column as 50 mm. And we also have to consider the effective length factor as 1.2. Including of all this data, some analysis data are also given. So actual load in column is actually 1600 kilonewton and the moment about the major axis. So for the column we are having the two axes. One is your axis XX, another is axis YY. So your axis XX is your major axis and axis YY is your minor axis. So moment about the major axis, that is X, is given as 45 kilonewton meter and moment about the minor axis is given as 40 kilonewton meter. As in the problem statement, we have given that floor to floor height is 5.6 meter. So total length or total height of your column is actually 5.6 meter, or you can say it is the floor to floor height. But we need to have the unsupported length of the column. So first of all, try to understand what does mean by the unsupported length of the column. So for better understanding, have a look over this figure. So this is your foundation and this is your slab and then it is the another slab. So from top of this slab to next slab, this is what floor to floor height, and this floor to floor height we actually have given as 5.6 meter. But our intention is to find out the unsupported length of your column, and that unsupported length of your column will be from the base of your beam up to the top of this slab. So this is actually the distance. This distance will give you unsupported length of your column. So how you can calculate this unsupported length of your column? That is very simple. We are having the total floor to floor height as 5.6 meter and we also have the depth of the beam. The depth of the beam we have given as 400 mm. That is going to become 0.4 meter. Look at your problem statement. We have given that the size of the beam as 230 by 400 in depth. So if you are going to subtract this 400 from the floor to floor height, so you will get the unsupported length of your column. So 5.6 minus 0.4 value, that will give you the unsupported length of your column as 5.2 meter. After all of this, what next? We also have given the effective length factor. So representing it by K. So effective length factor for the column as given as 1.2. Thereafter, effective length of the column about both axes. So if you want to calculate the effective length for the column about the axis X, about the axis Y, so you have to multiply unsupported length of your column with the effective length factor. So to actually calculate the effective length of the column about both the axes, we need to have the unsupported length of the column and we need to have the effective length factor. So about X and about Y, we are going to calculate the effective length of column, that will become 1.2 multiplied by 5.2. So that is going to become 6.24 meter. So this is actually the effective length of your column about both the axes. So on later stage, we need to have this value for further calculation. Now let's start the design. So in the first step, we are going to see the classification of the column as per IS 456-2000, clause number 25.1.2, page number 41. So if you are going to see this clause in your IS 456, so this clause is going to define the type of the column as short column or long column. So a compression member may be considered as a short column when both the slenderness ratio are less than of 12. So we are going to see this ratio, effective length of the column about x axis divided by overall depth. this ratio we have to check whether it is coming more than or less than of 12, or also we have to check effective length about the y-axis divided by overall width of your column, whether it is coming more than of 12 or less than of 12. So if the ratios are coming more than of 12, so we can say that in that particular axis or about that particular axis your column is long column, or about that particular axis your column is short column. If about both of the axes, if the ratio is coming more than of 12, then we are going to call it as slender or long column. But if about both of the axes, if these ratios are coming less than of 12, we are going to call it as it is the short column. So in our proposed example, we have to do the same calculation. So in the proposed example, the effective length of the column about x-axis is 6240 divided by overall depth of your column as 500. So this ratio comes out to be 12.48, which is greater than of 12. Hence, it is a long column about x-axis. Likewise, we are going to do the calculation for y-axis. So effective length about the y-axis is same as that of your x-axis, 6240 divided by width of your column is 300. So this ratio comes out to be 20.8, which is again greater than of 12. Hence, it is the long column about y-axis also. So overall, the proposed column is a slender or long column about its both axes, as major axis as well as minor axis. Now, after deciding that the column is long column about both of the axes, so that's why we have to proceed with the second step, where we are going to do the calculation for the additional moment about the both axes due to long column effect. So if your column is going to become long column, so due to long column, we need to add some additional moment where specified by your code IS 456-2000 clause number 39.7, page number 71. So if you are going to see this code for this particular clause, so here the equation is given to calculate the additional moment about the x-axis, additional moment about the y-axis. Or in another way, you can say the additional moment about the major axis, additional moment about the minor axis. So this calculation we are going to do in our proposed example. So here the additional moment about the x-axis, the formula here it is given what? Pure axial load coming to your column multiplied by overall depth. Because actually we are going to do the calculation about the major axis as x. So resisting depth is what? This overall depth. If you are going to do the calculation about the y, so resisting width is going to become what? This width b. So this pure axial load multiplied by overall depth divided by 2000 multiplied by effective length about the x-axis divided by overall depth is square of this complete value. So if you are going to put all the values in this particular equation as pure axial load, here it is given as what? 1600 kilonewton. So that I am going to put here as pure axial load as 1600 kilonewton multiplied by overall depth of your column as 500 divided by 2000 multiplied by effective length about the x-axis. So effective length about the x-axis is what? 6.24. In mm it is going to become 6240 divided by overall depth. Square of that. If you are going to do the calculation for these values, so we are getting the value as 62.3 kilonewton meter additional moment about the x-axis. Likewise, we have to do the calculation for the y-axis. So we are getting the value as 103.834 kilonewton meter. So these two values are actually the additional moment, and the basic moment analysis results values are actually given here. Basic analysis results 45 kilonewton meter and 40 kilonewton meter about the y-axis, and these two values are actually the additional moment about x-axis and about y-axis. After calculating the additional moment about both the axes, we again have to look at the recommendation were made by your code. So code has specified that you have to apply the moment reduction factor for this additional moment. So when you are looking at this clause 39.7.1.1, so this code has suggested that the value given by the equation 39.71. So whatever the value you have calculated by this equation 39.71 max and may. So whatever the value you are getting here, so you have to multiply this value with the value of k. So may be multiplied by the following factor as k. So this k is nothing but the moment reduction factor, and this is calculated by this equation puz minus pu divided by puz minus pb. So how to calculate the puz? It is defined in the 39.6. So when you are going to see the clause number 39.6, so here it is what the equation has given to calculate the puz. So we are going to use this equation for calculating the puz value in our proposed example. So here in our proposed example, we are going to use the same equation. But to calculate the PUZ, we need to consider the percentage of reinforcement in your column. So here I am going to assume that the percentage of reinforcement in the column as 3%. So if 3% of reinforcement in the column is present, so the gross section size of your column is what? 300 by 500. So I would like to calculate the total area of the column. So we are getting 150,000 mm square is the total area of your column. Now area of the reinforcement in the column, so it is what? The 3% of your total area of your column. So 4500 mm square is the area of the reinforcement in the column is present if you are going to consider 3%. Now area of the concrete, actually if you are going to see complete column, so column is what? Total concrete. In that 3% of area of reinforcement is present. So I would like to subtract area of the reinforcement from the total area of the column. So total area of the column minus area of the reinforcement. So we are getting the 1,45,500 mm square area of your concrete is there only. So if you are going to put all the values in this equation, PUZ 0.45 FCK, characteristic strength of your concrete, multiplied by area of the concrete plus 0.75 yield strength of your proposed steel, multiplied by area of steel in your concrete or in compression. So 0.45 multiplied by 30 is your grade of concrete, multiplied by concrete area plus 0.75 yield strength of your proposed steel, multiplied by 4500 area of your reinforcement. So here we are getting the value as the pure axial load as 3364.875 kilonewton. So this value we got. Second, we also are knowing the value of PU. The pure axial load coming to your particular column is what? 1600 kilonewton. Divide by PUZ. Now unknown thing is what? PB. What does mean by this PB and how you can calculate PB, that we have to see. So this PB for both of the axes will be different. PBX we have to calculate, PBY we have to calculate. So come back to your proposed example. So now we have to find out the value of PBX and PBY. These two things are unknown to calculate the K value. So how to calculate this PBX and PBY? For that we need to do the calculation. So first of all, we actually have given the effective cover. So effective cover for the column as what? 50 mm. About x-axis D dash by D, we are getting this ratio as 0.1. About y-axis D dash by B, we are getting 50 divided by 300 as the value of 0.167. Why we are doing this calculation, you will come to know on later stage. So here we actually have to find out PBX and PBY. So to find out PBX and PBY, we have to find out the value of K1 and K2. For that we need to refer the SP16 table number 60. Look at this table number 60 of SP16. So for rectangular section, PB divided by FCK B into D is equal to K1 plus K2 percentage of steel divided by FCK. So this is the equation to calculate the PBX or PBY. So here unknown thing is what? K1 and K2. Basically we have to do the calculation for K1 and K2. So how you will get the value of K1 and K2? So values for the K1 and K2, two tables are actually here given. Table first, values for K1, and table 2 for the values for K2. So for the section rectangular circular, what type of the section is there? What type of geometry of your column section is? So it is rectangular or it is circular. So our proposed section of the column is what? Rectangular. B into D or D into B. Now here D dash by D value you have to calculate. We already have calculated this value as D dash by D about x axis. So we are getting the value as 0.1, this ratio. So when you come to see SP16 table number 60 for the K1 value, so D dash by D is what? 0.1. And for rectangular section, what value we have to consider? 0.207. So that I am going to put here as for K1 0.207. For x-axis, K1 value 0.207. What about the K2? So how to calculate this K2? So for K2, multiple values are there. D dash by D for 0.1, 0.05, 0.1, 0.15, 0.2. So what our value is, D dash by D is 0.1 directly. Okay. So again, I need to come here for K2 rectangular section. Now equal reinforcement on two opposite sides. Rectangular section, equal reinforcement on four sides. Actually here you have to decide what type of the provision in your column you would like to do. So here two options are there. Either you can provide the reinforcement on all four sides, or other option is what? you can provide the reinforcement only on two sides, on this side only, on this side only. So here I am going to assume that my provision of the reinforcement will be on two opposite sides only. So this we have to consider what grade of steel is there, 415. So for this grade we have to consider the value as d dash by d as 0.1, and for that we are getting the value as 0.082. So that I am going to put here as 0.082. So if both of the values you are going to put in this equation as Pbx divided by FCK B into D is equal to K1 plus K2, PT is the percentage of steel in your column divided by FCK. If you are going to put all the values in this equation, so we are getting the value of Pbx as 968.640 kilonewton. Likewise, we have to do the calculation for y-axis. So for y-axis, what is the value of d dash by b? So it is 50 divided by 300. We are getting the value as 0.167. So when you come to see SP16, table number 60, so d dash by d for rectangular again. Now at this time, our value is how much? Our value is 0.167. So it is not exactly 0.1, it is not exactly 0.15, it is not exactly 0.2. It is coming in the range of 0.15 and 0.2. So we have to do the linear interpolation between these two. If we are going to do the linear interpolation, so we are getting the value of K1 as 0.192. Likewise, we have to do the calculation for K2. So when you are going to see SP16, table number 60, so again for the K2, we are getting the value in between of 0.15 and 0.12. This will be the range, and rectangular section equal reinforcement on two opposite sides. For 415, so we have to do the interpolation between these two values. So after doing the linear interpolation, we are getting the value of K2 as 0.023. So if you are going to put these two values K1 and K2 in this equation, so we are getting the value of PBY as 874.35 kilonewton. So after all of this, finally we have to calculate the moment reduction factor as Kx and Ky. The same equation we have to use which is given in your IS 456. This K value, moment reduction factor about x-axis, moment reduction factor about y-axis, this equation we have to use. So that I am going to see by the calculation. So you have to put the value of PUZ. How much we have calculated PUZ? It is actually 3364.875. That I am going to put here, minus pure axial load is 1600, analysis value divided by PUZ again, minus PBX. First time we have to put the PBX. After doing the calculation, we are getting the value of 0.7365, and KY value we are getting as 0.7089. So the code has specified that this K value should be less than of 1. So by the calculation we are getting both of the values are less than 1, means that our calculation is what? Correct. Now you have to multiply this Kx value with the additional moment. Okay, so additional moment we have calculated about x-axis 62.3. So we have to multiply this 62.3 with the moment reduction factor about the x-axis. So here 0.7365 multiplied by additional moment about x-axis, we are getting the value of additional moment finally 45.884 kilonewton meter. Likewise for y direction, you have to multiply this reduction factor with the additional moment about the y-axis as 103.834. So after doing the calculation, we are getting 73.607 kilonewton meter is the additional moment about y-axis. So these two values are the final additional moment about x and y. Now in the third step, we have to do the finalization of the initial moment from the analysis moment and moment due to minimum eccentricity criteria were specified by IS 456-2000. For better understanding of this third step, have a look over this. So here we are having different types of the moments. One moment that is coming from the analysis results, another moment that we have to calculate based on the eccentricities criteria, and third moment that we have calculated due to long column effect. So actually we have to compare the initial moment due to analysis results and moment due to eccentricity criteria. So among these two values, we have to consider the maximum one. Whatever the maximum value in a particular direction, either in x or either in y, in comparison of moment due to analysis results, moment due to eccentricity. So which one the maximum you are getting, that we have to consider as the final one. And that final moment we have to add with the additional moment that we have calculated in that particular direction. And that will be the final design moment for which we have to design our particular column. So we are going to look at IS 456-2000 clause number 25.4. Here it is suggesting that how to calculate the eccentricity in a particular direction. So all columns shall be designed for the minimum eccentricity equal to unsupported length of that particular column divided by 500 plus lateral dimension of the column divided by 30. And in no any case you are allowed to consider the eccentricity less than of 20 mm. So if the calculated value you are getting less than of 20 mm, so at that time you have to consider at least 20 mm. But if the value you are getting more than 20 mm, so that calculated value, for an example 23, 25, that you have to consider. So if value is coming out to be more than 20, that you have to consider. But if the value is coming less than of 20, you have to consider at least 20. So we are going to do the same calculation with the same formula. So have a look over this in x direction. How much the eccentricity is there in x direction? So unsupported length of your column divide by 500 plus overall depth of your column divide by 30. So unsupported length of the column is how much? 5200. In the start we have done the calculation for calculating the unsupported length of your column. So unsupported length of the column is 5.2 meter, means 5200. So that I am going to put here as 5200 divided by 500 plus 500 divided by 30. So we are getting the eccentricity in x direction is 27.06, which is greater than 20 mm. That's why we will consider the 27.06. If this value is coming less than of 20 mm, at that time we have to consider at least 20 mm. Now next, we have to do the calculation for the eccentricity in y direction. Again, unsupported length divided by 500 plus width of the column divided by 30. So after doing the calculation, we are getting the value of 20.4 mm, which is again greater than 20 mm. So we have to consider this 20.4. Now, movement due to eccentricity in x direction. So axial force multiplied by eccentricity in x direction. Axial force is what? 1600 multiplied by 27.06. So we are getting the final movement in x direction as 43.296 kilonewton meter. Likewise, we have to do the calculation for y direction. Axial load multiplied by eccentricity in y direction. So we are getting the value of 32.64 kilonewton meter. So these are the movement due to eccentricity. Now we have to compare these movements with the movements due to analysis results. So the movement due to analysis results is what? Movement in the x direction is 45 kilonewton meter. Movement in y direction is 40 kilonewton meter. That is given in your problem statement. The analysis results for the movements are 45 kilonewton meter about the major axis, that is what? X direction. Movement about the minor axis, that is y direction, is 40 kilonewton meter. So we have to compare these analysis results movements with the minimum eccentricity movements. So like here, movement due to eccentricity is what? 43.296 in x direction, and due to analysis result is what? 45. So among these two values in x directions, which one we have to consider? Maximum one. So I'm going to consider this is the final one, MUX. And for y direction it is 32.64, and due to analysis result it is 40. So again we have to consider this value 40. So here note is also given. Take the maximum of initial movements of minimum eccentricity and analysis results as a primary moment for the considered direction as x and y. So as I have earlier explained what to do for these two movements, you have to consider the maximum one. Therefore primary movements for x and y direction finally as 45 kilonewton and 40 kilonewton as the final movement in the x and y direction. Now we have to add the additional movement in the both the direction. So final design movement for both the direction. So for x direction, basic movement plus additional movement. So basic movement is what? 45 kilonewton meter plus 45.884. Additional movement in x direction after the reduction is what? 45.884. So that I am going to put here as 45.884. So we are getting the result as 90.884. Therefore, movement in y direction, basic movement plus additional movement. So 40 plus in y direction it is 73.607. I am going to put here. So final movement in y direction we are getting as 113.607 kilonewton meter. So this is the final movement for which we have to design our column in x and y direction, or about major axis or minor axis. Now come to the step 4, where we are going to check for the adequacy of the provided section and reinforcement. So basically in this step we are going to check whether the provided section size of the column and provided percentage of reinforcement is okay or not. For that, we need to look at the clause number 39.6 of IS 456/2000. So when you are going to see this, so there is a equation is given, and in this equation we need to have the applied moment over the section in both of the axes, as well as we need to calculate the moment resisting capacity of the section about both of the axes, and the addition of these two ratios that should be less than of 1. If this ratio comes out to be less than 1, at that time we can say that provided section size of the column and provided percentage of the reinforcement is okay. But in a situation when you are getting more than of 1, at that time the provided section is not safe, as well as provided percentage of reinforcement is not safe. You have to increase that. So here we are going to perform this check in our proposed example. So actually we earlier have calculated MUX and MUY. Now we need to calculate the moment resisting capacity of the section as MUX1 and MUY1. But before of that, we also need to calculate the alpha n value. This factor we have to calculate. So for calculating this alpha n, we are having the formula 1 plus PU by PUZ minus 0.2 divided by 0.8 minus 0.2. If we are going to put all the values in this equation, we are getting the value of alpha n as 1.459. Now next unknown thing is what? MUX1 and MUY1. For that, we need to take the help of SP16. In SP16, there are multiple charts are available based on D dash by D ratio and grade of steel. So in our proposed example, grade of steel is Fe415, and for X direction, for major axis, D dash by D value is what? 50 is your effective cover. Overall depth of your column is 500, so value comes out to be 0.1. So based on this D by D ratio as well as grade of steel, so grade of steel is Fe415. So I need to look at SP16. So in this SP16, see D dash by D and Fy. So Fy is what? 415, and ratio D dash by D is what? 0.1. If ratio D dash by D, if suppose 0.15, 0.2, so different charts are actually given for different ratio of D dash by D. But actually our calculated value for D dash by D is 0.1. That's why we are going to check this chart number 32. One more thing, here we have decided that we will provide the reinforcement on two sides only. Some other charts are also given where the reinforcement are going to be considered on four sides of the column. So this decision you have to take. Either you would like to provide the reinforcement on two sides, or you would like to provide the reinforcement on all four sides of the column. So here I am going to decide that the reinforcement I will provide in my column on two sides equally. So here, by considering the reinforcements are provided equally on two opposite sides. So D dash by D is 50 by 500, 0.1, and PT by FCK. So different charts are actually here given. Different curves are actually given based on PT by FCK ratio. This is what PT by FCK ratio. So it is 0, it is 0.02, 0.04, 0.06, 0.08, 0.01. So how much the PT by FCK? So percentage of steel we have considered as 3%, and FCK characteristic strength of your concrete is what? 30. So this ratio again comes out to be 0.1. Now PU by FCK BD. PU 1600 pure axial load into 10 raised to 3 in Newton divided by FCK is 30. Width of the column is 300. Overall depth of your column is 500. So you are getting this value as 0.355. Okay. So based on this PT by FCK, we have decided to consider this curve. Now PU by FCK BD value is 0.35 something. So 0.3 is this one and 0.35. So it is 2, 4 and 5 something here. So we have to project this line over this curve, and then this curve you have to project here. So this value comes out to be 0.11, 0.12, 0.13, 0.14 and 0.15. So in between 0.14 and 0.15 you can take the value. It is what? Approximation. So here I am going to take the value as 0.14. So that I am going to put here as 0.14. So after doing the calculation by keeping this value of FCK here, by keeping this value of B as 300, by keeping this value of overall depth as 500, and this ratio we are getting 0.15 from the chart. So finally we are getting the resisting capacity of the section as 315 kilonewton meter. Likewise, you have to do the calculation for minor axis or for the y axis. So here D dash by B, 50 divided by 300, we are getting the value as 0.167. So if we are going to find the chart for D dash by B or D dash by D
as 0.167, so you will not get any chart. So we have to round up this value. So I am going to round up this value as 0.2. So the chart for 0.2 is actually available. So I am going to look at Fe415 grade of steel and d dash by d value as 0.2. That I am going to consider. Now here again Pu by FCK BD value will be same 0.355. So again we have to look at the same 0.35 here somewhere it is, and 0.1 value we are getting here. Now just project it down. So we are getting the value of mu by FCK BD square as 0.12. So that I am going to put here as 0.12 mu y1 divided by FCK. Now at this time D will be alone and B square will be, okay, because it is about y axis, okay, or about minor axis. So after doing the calculation, we are getting the value of mu y1 as 162 kilonewton meter. Now we are having all the values to put in this equation as mux design moments, mux and muy divided by mux1 moment resisting capacity of the section alpha n value. Put all the values in this equation. So after keeping all the values in this equation, we are getting the addition of these ratios as 0.759. So as the code has suggested that if this value comes out to be less than of 1, at that time we can say that our provided section size and our provided percentage of reinforcements are adequate, or we can say it is safe. If this value comes out to be more than of 1, at that time we need to increase the section size. We need to increase the percentage of reinforcement. So our design is what? Okay. Our section size is okay. Our percentage of reinforcement is okay. Now finally area of reinforcement available in column as 3%, area of steel in compression, area of steel in concrete 3% divided by 100 multiplied by overall section size of your column. So area of reinforcement we have to provide in the column as 4500 mm square. Suppose I am going to assume that I will provide the 28 mm diameter of bar. So if I am going to provide the 20 mm diameter of bar, so unit area of 28 mm diameter of bar is what? 615.75 pi by 4 d square. D is your diameter of bar. If you are going to put 28 here, 28 square, so you are getting the value of 615.75. Now, how many number of bars are required to provide in a column of size 300 by 500? How many number of bars I need to provide? Being a diameter of bar as 28, so number of bars are required to provide as total area required. How much the total area required? 4500. So I have to correct it. Actually, it is wrong. 4500. We are getting the ratio as 7.308. So we have to round up this value as 8 number of bars I am going to provide of diameter 28 mm. So this is about the design for the main reinforcement in your column. After the complete design of the main reinforcement, now in this step 5, we have to do the design for the lateral ties or lateral reinforcement. For that, we need to look at IS 456-2000 clause number 26.5.3.2, page number 49. So when you are going to see this clause of IS 456, in the first recommendation, the code has suggested what should be the spacing between the two lateral ties. And in second requirement, here it is what suggested that what should be the diameter of the lateral ties. So diameter of the polygonal links or lateral reinforcement shall not be less than of 1/4 of the diameter of largest bar. So here we have decided to provide the main reinforcement of diameter 28 mm. So 1/4 of 28 mm. So it is coming out to be 7 mm. So your diameter of lateral ties should not be less than of this 7 mm. That's why we are going to provide the diameter of the lateral ties as 8 mm. After that, we have to decide the spacing, vertical spacing between the two lateral ties. So for that, 3 requirements were suggested by your code. Where first requirement is that the least lateral dimension of the compression member. So our section size of the column is what? 300 by 500. So least lateral dimension of the column is what? 300. That's why I am going to put here as what? 300. Second, 16 times the diameter of main reinforcement. Here suggested that second 16 times the smallest diameter of the longitudinal bars. So if suppose you are using the different diameter of the main reinforcement, like suppose in an example you are going to provide the 16 mm diameter bar also and 28 mm diameter of bar also. So you have to take the smaller diameter of bar. So 16 times 16. But here 2 diameter of bars are not available. Only 1 diameter of bar is there as 28. That's why 16 times 28, that is coming out to be 448 mm. And third, in no any case, your spacing should be more than of 300 mm. So that I'm going to write here as third requirement as 300. Now overall, among these three recommendation, your spacing should not be more than of these. Always your spacing should be less than of all these three values. So here you can take the value of 300. Maximum you can take the value as 300. Beyond of that you cannot provide. So that what here I am going to consider the 8 mm diameter of bar at a spacing of 250 mm. Actually you can provide the 300 also, but for the safety concern I am going to provide the horizontal reinforcement or lateral ties at closer spacing. Okay, so that's why more number of rings will be there, more reinforcement will be there, so our design will be more safe. So that's why what I'm going to do, if you are taking the 300, that will also be okay, but for the safety concern I'm going to take 250 mm center to center. So this is for the design for the lateral reinforcement. So after the completion of the design, we have to prepare the schedule and detail as per your design results. So overall section size of the column is what? 300 by 500. Main reinforcement, that is your vertical one, is what? 8 number of bars of diameter 28 mm. Then lateral reinforcement is of 8 mm dia at a spacing of 250 mm center to center. Here you can see in the figure, the lateral reinforcement is actually present here, and the spacing between the two lateral reinforcement is what? 250 mm center to center. And this is what sectional view of your section as 300 and 500.
Welcome you all in ISO certified live training program, ETABS, RCDC and Excel that makes you a professional structural engineer. In this training program, you will learn everything about ETABS and RCDC from basic to advanced. Real life project of medium rise structure from architecture plan to final design sheet. Real life project of high rise structure with all advanced topics. Design of structural elements using advanced Excel sheets. Have a look over the features of this training. Daily live classes conducted by expert for 1.5 hours. Recording of every session with lifetime access. Can interact with expert anytime, 24/7. Exposure to real practice. ISO certification of training completion. It's 5-star rated training program. Till now, more than 1,000 participants have benefited from this training program. Now you are the next. Hello everyone, welcome you all in a new ISO certified live training program. Design of substructure using CSI Safe Excel and manual. In this training program, we will learn all about the concept of substructure design, commands in CSI Safe software for the substructure design, validation of CSI Safe result with your manual and advanced Excel sheets. This training program will cover 4 real life projects. In the first and second, we will cover all the types of isolated foundation in CSI Safe software. In the third real life project, we will cover the raw foundation. And in the fourth real life project, there will be the coverage of pile and parapet design, design of basement wall. And at the end of this training program, we will learn how to prepare the final design sheet for the site execution. Have a look at all the features of this training. Daily live classes conducted by expert. Recording of every session. Can interact with expert anytime. Exposure to real practice. As a certification of training, it's 5-star rated training program. Till now, more than 1,000 participants have benefited from this training program. Now you are the next.